Hello guys, today I'd like to talk to you about a very important term called acceleration. This is a term that some of you have probably heard before, but many of you may not know exactly what the term means. So your goal today is to make sure you understand what it means, when it happens, and how to determine it mathematically from a graph. Okay, so let's start with what it means. Acceleration refers to the rate at which your velocity changes. The rate at which your velocity changes. Here's how you find it. You get the change in your velocity and you divide by time, the very definition of a rate. It's how quickly your velocity is changing. It's called acceleration. So anytime your velocity changes, you're accelerating. So as we watch the school bus take off from its original resting location, you can see it getting faster and faster and faster to the right. That would represent a positive acceleration. It's gaining speed to the right. We can see with our train that it also is accelerating. You can see it getting faster and faster and faster. If we're using the convention that left is negative, this would actually be a negative acceleration even though it's getting faster because it's accelerating, gaining velocity to the left. Here's another example. You can see really clearly this athlete accelerating along the ramp on her way to doing a long jump. She starts out at rest. She gets faster and faster and faster. And when she hits her top speed, she's going to jump as far as she humanly can. Here's another example of acceleration. This time, instead of getting faster, this object's going to get slower. So this is a test of the braking system on this truck. And you can see it was able to slow down really quickly. Again, missing the fake car, the test car, by just a few centimeters. So again, this would be a negative acceleration because it is slowing down, moving to the right. Okay, here's the last example, and this is one's going to be a little bit tricky. Remember, the velocity is not just speed, it also includes a direction. So anytime your direction changes, you are also accelerating. So if you watch down here, you can see that this car is going around 100 miles per hour, and it will go 100 miles per hour for the entire time. But it's going around the turn. So the direction it's traveling changes, and that is also an acceleration. If you think about it, anytime you accelerate, you can feel it. That's what makes acceleration different from just a constant velocity. When this person was in their car going around that turn, they would feel themselves being thrown toward the outside of the car. When the people were on in the truck and it started accelerating, they would feel themselves thrown forward. And when the people were on the train, they would have felt themselves moving backwards as the train moved forward. Accelerations you can sense with your body. Velocities you cannot. Okay, so again, you find acceleration by figuring out how much the velocity has changed, and you divide by the time it took to make that change. So for instance, with this car, this Hyundai Genesis, it can go from 0 to 60 in 5.7 seconds.
The new 375 horsepower Hyundai Genesis can go from 0 to 60 in 5.7 seconds, even faster than a Porsche Boxster. Which means, if it starts now, it will reach 60 miles an hour. Now.
So oftentimes when you're trying to buy a car, the people selling you the car will tell you how good it is at accelerating. It's not just important for race cars, but if you're on the highway and you need to go around someone, you want to make sure that your car can accelerate at a pretty rapid rate. So let's figure out the acceleration of that car. So we start out with our formula, change in velocity over time. It can go from 0 to 60 in 5.7 seconds. So for change in velocity, you'd go 60 minus 0, final minus initial. For time, you'd go 5.7 minus 0, again, final minus initial. When you divide it out, you get 10.5. And here's where acceleration gets a little bit tricky, the units. Think about it before I tell them to you. What units would this have? Well, hopefully you see that this 60 is miles per hour and the 5.7 is seconds. So the unit is 10.5 miles per hour per second. And although that sounds really cumbersome, if you think about it carefully, it might make a lot of sense to you. It says that the car is gaining 10.5 miles per hour every second. So the car would start out at a speed of 0, and then after 1 second, it would be up to 10.5 miles per hour. After another second, it would be up to 21 miles per hour. Every second that goes by, it gets faster by 10.5 miles per hour. That's what this means. 10.5 miles per hour each second. Okay, here's an example of somebody at Atco Dragway. They're going to wait for the light to turn green, and then they're going to accelerate as rapidly as possible. If we were to graph their motion, we know it would look like this. We saw this before. Position versus time gets steeper and steeper and steeper as they get faster and faster and faster. If we wanted to use this graph to figure out how quickly they were accelerating, it gets a little tricky. What you'd have to do is you'd have to find their speed at a given time, let's say 3 seconds, find their speed at a different time, this time let's say 7 seconds, and then use those two speeds in your acceleration formula, final minus initial, divided by the change in time, and we would get an acceleration of 5.6 meters per second per second. I'd like to emphasize at this time that this is the preferred, in fact it is the international standard for acceleration. Anytime we're doing any serious scientific work, we should be measuring our accelerations in meters per second. Okay? This is a pretty cumbersome process, so a better way of attacking this is when you're watching this person on their motorcycle, instead of tracking their position, you track their speed. So we'll do it with this car, and you'll notice instead of position here, we have velocity. We have to reorient our brain. This graph is no longer showing where the car is, it's now showing how fast it's moving. So you should draw this graph out in your notes and make sure you understand what each of these regions represent. Okay? This first region, for the first maybe second and a half, represents when the car had no velocity. It was at rest. Now you can see the velocity getting larger. This is where the car is accelerating. Now the car is going at a steady velocity of about 20 meters per second, and now it has a negative acceleration. It's slowing down. And finally, the car is at rest again for maybe the last 6 seconds. So when you see this graph, you should be able to tell what the car is doing. Now when you want to find acceleration, it turns out that it's really easy if you're doing a velocity graph. You don't have to go through all the nonsense we just did. Instead, you just pick two easy to read points on your graph and you find the slope. The slope will be the change in y, which is the change in velocity, over the change in time, and lo and behold, that's acceleration. So to summarize, acceleration tells how quickly your velocity is changing. Your velocity can change because you're speeding up, slowing down, or changing direction. And you find your acceleration by doing delta velocity over time. I hope this all made sense. If not, please go back and watch again. Pause when you have to, and make sure you understand this very important term.